Hello everyone. So this here is part 6 of subtopic 3.1. So the outcome for part 6 will be to describe and explain the white light pattern produced by a grating, and transmission diffraction grating can be used to analyze spectra of various light sources. Okay, so the first thing is white light. We know white light is made up of 7 colors. So to explain the white light that passes through a diffraction grating, what we need to do will be basically explaining about the two extreme ends. Basically, red light, which has a lambda of 700 nanometer, and violet, which has a wavelength of 400 nanometer. The rest of the colors lies within red and violet. So in this case, when I shine white light through a diffraction grating, I just explain about what happens to the red and the violet light. Okay, on the perpendicular bisector, what I would observe will be white light. So the reason is why would I see white light? And the reason is because on the perpendicular bisector, which is known as your zero order constructive interference, m equals to 0. So irrespective of whatever lambda is, you find that the path difference is equals to 0. So all light will reinforce constructively on the perpendicular bisector. Okay, between violet and red, which color will be closest to the central white, to the perpendicular bisector, or the central maximum? Which color between violet and red? So the answer is actually violet. And this can be explained again by this formula. Because when we compare the wavelength of violet light, it's much smaller as compared to the wavelength of red light. So violet light has a lambda of 400 nanometer. So in other words, the smaller the lambda, the smaller the angle sine theta. So therefore, theta will be smaller. And red light will be furthest from the central maximum. And the reason is because red light has the largest lambda. So the rest of the colors, the rainbow colors, will be located within red and violet. So for the second order, it's the same. Since violet has the smallest lambda, it will be closest to the central. Red, that has the largest lambda, will be furthest from the central. But an interesting fact will be violet third order will appear closer to the central than second order red. So to explain this, okay, let's put numerical values into this formula, right? So in order for me to see the second order red light is 700 nanometer, you find that m lambda is 2 times 700 nanometer. So from here, right, we can see that since D is constant, we are using the same diffraction grating both for violet and red light. We find that sine theta is just proportional to m lambda. So the greater m and lambda, the greater the sine theta. So if greater sine theta, the greater the angle theta. So from here, right, we can see that the second order of violet will give us an angular position that is larger than the third order of violet. So this is where the pattern starts overlapping with one another. Okay, so let's try this example. At what angles would a light source of 400 nanometer overlap with light source of 600 nanometer for a diffraction grating of 1000 lines per cm? So the answer is give the 3 lowest angles. So basically what this question wants, right, is to find at what angle would blue light overlap with green light on this point on the screen. Right? So when you use blue light and green light, they overlap at the same location. So give the 3 lowest angle in which they will overlap. Okay, so pause this video for 5 minutes and try to find the 3 lowest angles before starting this video again. Okay, so the question is, which order of blue would overlap with which order of green light? Okay, let's find D. We know there's 1000 lines per centimeter. So what's the slit separation? So the slit separation will be 1 over 1000 per centimeter. That means we times 10 to the power of negative 2. So this will give us 1 times 10 negative 5 meters. Okay, using this formula, d sine theta equals to m lambda. If we see, right, for a diffraction grating, since they overlap at the same location on the screen, that means theta is actually the same. So if theta is constant, sine theta and d sine theta would basically be a constant for both lights, all right? For both different lambda, d sine theta is a constant. So if d sine theta is a constant, right? Cos theta is constant, they overlap at the same location for blue and green. So if d sine theta is constant, we can say that m1 lambda 1 equals to m2 lambda 2. So m1 will be the m order of lambda 1 is going to overlap with the m2 order of lambda 2. So it's not necessary this must be 1, this must be 2. It can be 1, this can be 5. All right? It's not necessary. It must be adjacent number. So rearranging m1, m2, lambda 2, lambda 1, because if we cross multiply, we get back this term. All right? And substituting the value of lambda. And simplifying 3 over 2. So in this case, m1 is 3. That means it's a third order of 400 nanometer. Is going to overlap with the second order of 600 nanometer. Because lambda 2, if you take as 600, and m2, you see m2 is actually 2. So this tells us that the third order of 400 nanometer would overlap with the second order of 600 nanometer. Okay. So in this case, the second time that overlap is at, it can be the third order of 400 nanometer divided by d. So we find what is theta 2. So theta 2 would be 6.89 degrees. Or we can take the second order of 600 nanometer divided by d. We'll get the same answer, same angle. The third time they overlap is at 6th order of 400 nanometer divided by d. So from here, we find that the third time they overlap will be 13.88 degrees. So the first time they overlap will be when theta is 0. So irrespective of whatever lambda it is, all right, when theta is 0, they will all overlap constructively at the perpendicular bisector. So the second time they overlap will be at 6.89 degrees, and the third time they overlap will be 13.88 degrees. Okay, so reflecting back again, describe and explain the white light pattern produced by grating. And transmission diffraction grating can be used to analyze spectra of various light sources. So it can be used to analyze white light. Okay, next is determine from the distance between the slits to the grating the maximum number of orders possible for a given grating and wavelength. So what does this mean? Okay, for a diffraction grating, we know that d sine theta equals to m lambda. So for a given type of grating and a given type of lambda, this question wants us to find the maximum number of orders that can be emitted from this grating. So we want to set m to be maximum. So in order for m to be maximum, then sine theta has to be maximum. And when is sine theta maximum? Okay, if we plot the sine function, right? When is sine theta maximum? Basically, when it has a value of 1. Or in other words, when theta is 90 degrees. So in other words, this can be simplified as d sine 90, which is 1, equals to m lambda. So you want to find the maximum number of orders for a particular wavelength passing through a particular diffraction grating. I just have to equate m. The number of orders is d divided by lambda. Okay, let's see how to apply this in this example number 11. Okay, so pause this video for 3 minutes. Try to use the formula that we have just learned. To find the maximum number of orders, it's just d divided by lambda. Okay, so in this question, a diffraction grating contains 4,000 slits per cm, is illuminated with electromonochromatic light, and it produces a second order bright light at 30.3 degrees. All right. So A, what's the wavelength of the light used? And B, what's the maximum number of orders emerging from this grating? Okay, the maximum number of wavelength is we use the diffraction grating formula. First of all, find the slit separation. So 4,000 slits per centimeter. Then to find D, 1 over 4,000 per centimeter times 10 negative 2. So this will give us 2.5 times 10 negative 6 meters. Next, use the diffraction grating formula, d sine theta equals m lambda. So second order bright fringe, right? So this will lead us to identify that m equals to 2. So find the wavelength. So wavelength is d sine theta over m. Substituting m to be 2, we got d, we got the angle. We can find that lambda is 6.31 times 10 to the power of negative 7 meters, or 631 nanometer. Okay, so for B, what's the maximum number of orders emerging from this grating that has 4,000 lights per centimeter when we use a light source of 631 nanometer? So to solve this, we set theta to be 90 degrees. So in other words, d sine theta, which is m lambda. So m equals to d divided by lambda. So we got d, we got lambda, we just substitute, and we get 3.96. So maximum number of orders will be 3. We don't round up. So in this case, right, remember m must always be an integer. It cannot be a fraction. So in this case, if it is a fraction, basically we don't see any light. We cannot see m, the fourth order of m. The reason is because for us to see the fourth order of m, that means theta has to be greater than 90 degrees, which is not possible. So we cannot round up in this case, right? We have to round down. Okay, so determine the distance between slit and grating, the maximum number of orders possible. Yeah, so we always round down. Okay, next is the formula d sine theta equals to m lambda can be used to analyze interference pattern and identify properties of a grating that makes it useful for spectroscopy. Okay, spectroscopy is basically to identify what's the wavelength of a light that comes in, all right? Let's say, for instance, if we have sunlight coming through, right, we want to see, okay, what are the wavelength that makes up sunlight? So that is spectroscopy. And the apparatus that we use is known as a spectroscope. So spectroscope, all right, consists of a collimator. So the function of a collimator is basically to collimate the beam. Okay, how does it do it? Okay, this is your spectral light. You have a spectral light that's placed at the end of this collimator, right? So this spectral light will emit light in all directions. So collimator consists of a series of lenses, right? That basically collimate the light beam. So when I say collimate, that means make sure that the light beam move parallel with one another, like what you see here. So this beam that is now collimated will strike a diffraction grating. And when that happens, the light will diffract. When the light diffract, you can pick up the interference pattern by looking through this telescope. So you place your eyes here through this eyepiece, right? You can see a crosshair, like the sniper's gun, right? This is a crosshair. Okay. The advantage of a spectroscope would be basically, right, the angle measurement, right, that you get is very accurate. See here, right, it's a this is all the angle that you see. and you can go up to a resolution of 1 minute. So you can measure 232 and 20 minutes, right? That's how accurate you can measure your angle from a spectroscope. So how it works is basically, all right, previously we have been describing, in order for us to see the interference pattern, we have to put a screen. So you can measure angle theta by measuring the fringe separation and measuring this distance L. But the problem with using a screen would be if you are trying to see higher order interference pattern, right? Your screen has to stretch all the way to infinite, right? So it's difficult to observe and measure higher order constructive interference. So that's where you have this spectroscope, right? So the spectroscope is basically replacing the screen with a telescope. So if you want to see, let's say, for instance, the blue line, right? What you do is you rotate the telescope, and when the blue line comes into view, you make sure that the blue line coincides with the crosshair in your eyepiece. So once that's happened, can you see the blue line coinciding with the crosshair? You can measure your angle accurately from this vernier scale, right? Next, when you want to observe the red line, you move your telescope further. And when you see the red line coinciding with the crosshair, you can again measure your angle accurately. So the advantage of a spectroscope will be you see clear, distinct lines. You get very clear, accurate measurements of angle theta. Okay, what do you mean by clear, distinct lines? Okay, let's take for instance, this here is the image that I will see from Young's double slit experiment, right? Remember the intensity distribution? So you want to measure, let's say, constructive interference. So I move my eyepiece, all right, to this point where I think it is now the maximum. Whereas if I'm doing it for diffraction grating, what I see will be clear, distinct lines. It's not spread out like what you see for Young's double slit. You see clear, distinct lines like that. So you want to measure the first order of rate. I move my crosshair so that the crosshair coincides with the line, the red line. So I can clearly identify that this here is my constructive interference. But here, right, I cannot clearly define, is this exactly the maximum? Or is it slightly towards the left or towards the right? Of course, the maximum or the light intensity looks the same. So this is what it means, right, for advantages of a grating in spectroscopy is that you see clear, distinct lines like this. So angle measurements can be measured accurately because you can measure up to 1 minute accuracy. And there's a formula to that, calculate lambda. So you can measure theta accurately. You can know D accurately from your diffraction grating. You can observe a first order or second order or third order clearly. So with this, you can use this formula to calculate what is lambda. So spectroscopy would be basically the science of studying and identifying what is the wavelength of this electromagnetic wave. Okay, so this is the end of part 6.